Hello everyone and welcome to part 5 of lecture 13 and 14. In this part of the lecture we are going to look at an example to practice some of the concepts that we learned in previous parts. So here we have an example in which methane is being burned at 25 degrees centigrade, and we are provided with air at 25 degrees centigrade, and we need to calculate what is the theoretical flame temperature of your furnace. Okay, so to do that we need to perform an energy balance to calculate what kind of heats are involved in the system. And in order to calculate, or in order to perform a heat balance, first we need to see what kind of components are involved. Okay, so we look at the chemical reaction. So we have methane, and the methane is being burned by providing air or oxygen. So in this case, obviously we are writing oxygen because we are looking at the reaction equation. So 1 kilomole of methane requires 2 kilomole of oxygen, and as a result of this combustion reaction, we have 1 kilomole of CO2 and 2 kilomoles of water produced as combustion product. Okay. So now we know that to have a complete combustion of 1 kilomole of methane, we need 2 kilomole of oxygen. But obviously, we are providing air to the furnace. We are not providing oxygen. Okay, so we have to calculate what is the amount of air that we need to provide. So we can calculate based on the logic that the air is 21% oxygen by volume. It means that the 79% of this air would be nitrogen. Okay, so we can calculate the amount of nitrogen supplied to the furnace. That would be 2 times 0.79, because there are 2 kilomoles of oxygen, so there needs to be 2 kilomoles of nitrogen, and divided by the volume fraction of oxygen in air. So that gives us 7.52 kilomoles of nitrogen. Okay, so it means that we are providing 9.52 kilomoles of air. So based on this reaction, what kind of components will be present in our flue gas? So we can see that we will have nitrogen present that is coming from the air, and that will be 7.52 kilomoles. Then we have produced 1 kilomole of CO2, and we have produced 2 kilomoles of water. So that will be the components present in our flue gas. Now the next thing that we need to calculate is the enthalpy of the flue gas. And to calculate the enthalpy of the flue gas, we need to know what are the CPs of different components of your system, of your flue gas. And to know the value of CPs, we need to know a temperature value. Okay, so it means that before we even start to calculate the theoretical flame temperature, we need to know the value of theoretical flame temperature. Okay, that is a bit funny, but to do that, we have to make an initial guess of theoretical flame temperature, and here we are assuming a value of 2000 degrees centigrade. And this initial guess can come from literature, for example, based on what kind of fuel you are using, what kind of furnace you are using, and based on these parameters, you can make a well-educated guess. So here we have assumed 2000 degrees centigrade, and then using this table that I showed you in part 4, that was for example here, we can calculate or determine the value of CPs, mean CP, for different components. So for the case of let's say oxygen, at 2000 degrees centigrade we have 35.30. For nitrogen we have 33.16, and similarly for CO2 and water. Okay, and then we calculate the enthalpy of the flue gas given by this equation, that is the sum of the flow rate of different components times their CP times the temperature difference. Okay, and here we are taking a temperature difference from the flame temperature minus the ambient temperature, because the flue gas is going to go to the ambient. Okay, and if you put the values of different components here, so we have the moles of nitrogen, that is 7.52 kilomole, times the Cp, that is 33.16. Similarly, we have for the case of CO2, and then we have for water. Here we are not including oxygen because oxygen and methane were totally consumed in the combustion reaction, so we are just taking the combustion products. And then we multiply this whole term with the temperature difference, critical flame temperature minus 25 degrees centigrade, that is the standard value or the ambient condition. And we also know the standard heat of combustion for this reaction. Again, we have to look at literature, and from this table that I showed you in part 4, that if you burn 1 kilomole of methane, we produce 802.8 megajoules of energy. So if you use this value here, so we know how much standard heat of combustion is coming from the reaction. And then we have to calculate the heat content of the fuel and the air as well. So because our fuel and the air are provided at 25 degrees centigrade, so the enthalpy change compared with reference to the standard condition is 0, because both temperatures are 25 degrees centigrade, so this factor will be 0, and as such the enthalpy change will be 0. And if you perform now an energy balance, the heat that is taken up by the flue gas should be equal to the enthalpy of the fuel minus the enthalpy of the air minus the heat of combustion, standard heat of combustion. And if you put the values here, we can calculate the only unknown in this equation, that is the theoretical flame temperature, and we get a value of 2076 degrees centigrade. Okay, so this value agrees very well with our initial guess, and so it means that this value is acceptable. But if you have a theoretical a final value of theoretical flame temperature that is significantly different from your initial guess, let's say it's different more than 10%, then you have to assume another theoretical flame temperature and then do the iteration and or calculate it, and then find the final value, and then repeat the process until you have the convergence. Okay, so as I said in part 4 as well, in practice, the actual temperature is going to be lower than our theoretical flame temperature, because theoretical flame temperature is the maximum value of temperature that you are going to get from the combustion, because we are not assuming any losses. But in reality, we have different losses like heat loss from the casing, or we can have incomplete combustion, or we can have dissociation reactions where actually, because of very high temperature of the furnace, some of the components of your flue gas, they are going to dissociate. Okay, and most of these dissociation reactions are endothermic. It means that they are going to take some heat, and as such they are going to reduce your flame temperature. So what kind of dissociation reactions you can have inside your furnace? So for example, because of very high temperature, the components of your flue gas can break down. So you have CO2 that can break into CO and oxygen, and water that can break down into hydrogen and oxygen, and uh, several other dissociation reactions. Sorry, and all these dissociation reactions are endothermic. It means that they are going to absorb some heat of combustion, and as such it is going to decrease the flame temperature of your system. And that is why I said that the actual flame temperature in most cases is lower than the theoretical flame temperature. So here you can see a temperature enthalpy diagram where the red line represents the maximum flame temperature, or the theoretical flame temperature, and then you have the blue line that shows you the actual flame temperature. And the reason the actual flame temperature is lower than the theoretical flame temperature is because you have losses and dissociation reactions. So you might be thinking that why we are calculating the theoretical flame temperature if we are not going to use it. So the reason we calculate theoretical flame temperature, the first thing is that it gives you an actual amount of heat that you are going to get from combustion. And second thing is that it provides you a reference point to calculate the actual flame temperature. So in most of the cases, the actual flame temperature is about 10% lower than the theoretical flame temperature if you consider complete combustion. So by calculating the theoretical flame temperature, you can very well predict what is your actual flame temperature is going to be. Now let's have a look at another case in which we are provided with excess air to ensure that we have a complete combustion. So in this case, we know that we are provided with 15% excess air, and because we are burning methane, and if you remember from part 4, the table I showed you that if you are burning methane, you normally provide 5 to 15% of excess air, and here we are given 15%. So again, we start with our reaction. We are given this reaction. So we know that 2 kilomole of oxygen is required to burn 1 kilomole of methane, and now we have 15% excess air. So we need to calculate how much nitrogen will be supplied, and if there will be some remaining oxygen in the flue gases. So we know that air is 21% oxygen by volume, and using this logic, we can calculate how much oxygen is provided. So we have 2 times 1 plus 0.15, so that is extra 15%. So if you calculate it, we will be provided 2.3 kilomoles of oxygen, but we only require sorry 2 kilomole of oxygen in the reaction. It means that the remaining 0.3 kilomoles will be in the combustion product that will be in the flue gas. Similarly, we can calculate the amount of nitrogen supplied. That will be now 2.3 times the fraction of 0.79 over 0.21, and that should give us 8.6465 kilomoles of nitrogen. Okay, so because of this 15% extra air, we have extra amount of oxygen and nitrogen. So what will be in our combustion product or in our flue gases? So we have now remaining oxygen that is 0.3 kilomole. We have the nitrogen that is 8.6 kilomole, and then we have our CO2 form that is 1 kilomole and water form that is 2 kilomole. So again, we need to calculate what is the theoretical flame temperature. So we start by assuming an estimated value of theoretical flame temperature. Again, we start with 2000 degrees centigrade, and we do an energy balance to calculate the enthalpy of our flue gas using the same formulation that we discussed in case 1. And so we have, in this case, the difference is that we have the remaining oxygen present in the flue gas, that is 0.3 kilomoles, and then we multiply it with Cp of oxygen, and then we have a little bit extra nitrogen in the flue gas as well. The rest of the calculation is the same. So if you plug these values for other parameters, you get the enthalpy of flue gas that is given by this equation here. And then we perform an overall energy balance, and we know that from this equation that the enthalpy should be equal to the enthalpy of flue gas should be equal to the enthalpy of the fuel, air, and standard heat of combustion. And again, because we are at standard conditions, we take these two terms as 0, and we know delta H combustion just like the previous case from literature. So if you plug the values here in this equation, we get the theoretical flame temperature of 1852 degrees centigrade for the case when we have 15% excess air. Okay, so that is case 2, and if you compare it with case 1 where we do not have any excess air, so the theoretical flame temperature was 2076 degrees centigrade. Okay, so by providing excess air, you ensure that you have complete combustion, but at the same time, you also reduce your theoretical flame temperature as well. Now, the next thing that we need to look at is the furnace efficiency. And if you remember we discussed this slide in part 4, where we looked at that the furnace efficiency is the ratio of the heat that is transferred to the process fluid divided by the total heat produced by burning of the fuel. Okay. So to calculate the furnace efficiency, we need two temperatures. We need to know what is the theoretical flame temperature, that is we just calculated, and the second thing that we need to know what is the stack temperature. Okay, so if we know the value of stack temperature, we can calculate what is the furnace efficiency. So let's say that it is given to us that the stack temperature is 150 degrees centigrade for both of the cases that we just calculated, and we also know that the casing losses are 2%. So we can calculate the furnace efficiency, let's say for case 1, given by this equation. And if you expand this equation, we know that the heat that is gained by the process is equal to Cp of the flue gas times the temperature difference between the flame temperature and the stack temperature, divided by the Q fuel, that is equal to the heat of combustion times, and we can multiply it with the losses to the casing. Okay, so if we plug the values here again, this equation we know from the previous case, there we have Cp times 2076, that was the flame temperature for first case, minus the stack temperature, and divided by, we have the heat of combustion that is given to us from literature times the casing losses, and we get an efficiency of 92.1%. And now if you look for case 2, you can see that where you have 15% excess air, we have the Q process given by this equation, where the TFT is now 1852. We have the same stack temperature, and then we divide it by this value here, and then we have the efficiency of the furnace, that is 91.3%. Okay. So an important thing to notice here is that when we are providing excess air, not only we have a reduction in theoretical flame temperature, that like you can see here, that here in first case we had 2076, and that dropped to 1852, but we also have a reduction in efficiency from 92.1% for case 1 to 91.3 for case 2. Okay, so by providing excess air, we ensure that we have complete combustion, but at the same time we have some reduction in the efficiency of your furnace as well. Okay, so we have to consider these things, that what is an optimum value of excess air that we need to provide for our furnace. So decreasing the excess air will increase our TFT, as you can see here, and once we have increase in our TFT, we have for the same stack temperature, we will have less stack loss, and as such we have a higher efficiency. But we have to, as I said, we have to make sure that we are providing enough excess air to complete the combustion, because if you are not providing enough air, you will have incomplete combustion, and that is also going to reduce the efficiency of your furnace. Okay. Another way that we can increase the efficiency of your furnace is by preheating the air that you are providing to the furnace to burn the fuel. And this preheating of air will actually increase TFT, and if you increase TFT, again with the same logic, you will reduce your stack loss here. And most of the time we use the exhaust in the or the flue gas after the stack temperature to preheat the air. Obviously we have to be careful that if the dew point is low enough to give us some temperature here that we can use to preheat the air. So let's say if the stack temperature is here and then our dew point is relatively lower, then we can use this part of the exhaust gas to preheat the air and increase the efficiency of our furnace. But in case if your stack temperature is very close to your dew point, then obviously you do not have enough temperature driving force available to preheat your air, and then you have to either decide not to preheat your air or you have to use an external source to preheat the air to maintain a certain efficiency of your furnace. So just to summarize that the fire heaters are used in process plants when you require high temperature utilities and high heat duties, and the design of furnace very much depend on what is the application you are using it for, the type of fuel you are using, and how you are introducing air to the furnace. We also looked at the basic fundamentals of furnace in terms of radiant and convective sections, and we mostly talked about this type of furnace, but the fundamentals and the basic concepts are same for different designs of furnace as well. Okay, and we also said that the tubes can be mounted vertically or horizontally, and mostly for the case of cylindrical furnaces we have vertical tubes, but for the case of box type furnace we prefer to use horizontal tubes, but again it's a matter of choice and depend on the process design. And finally we looked at the concept of theoretical flame temperature and how we can actually calculate theoretical flame temperature and determine the efficiency of your furnace. So that is all for this lecture. Thank you for your time.